Hello, chemistry special agents. Welcome to lesson 3. So today's class will be about gases and thermochemical stoichiometry. So without further ado, we will talk about gases. The term gases should already be quite familiar to us because we know that, some gases like oxygen are essential for our survival. And we see these like, gas bubbles when we open up a can of Coke as well. But in order to understand what we're seeing, we need to understand their properties, which is low density and independent movement. Now, as you can see, the bubbles in this cup of Coca-Cola are expanding and occupying its entire container. So what does this mean? This means that each gas molecule must be able to move independently and move freely within an enclosed space. And that is why gases spread to fill its container easily. Now, scientists went on to develop a kinetic molecular theory to explain the things that we see for gases. So first of all, gases are made up of small atoms / molecules and move freely in space. And that was what we observed previously, where these molecules expanded out to occupy the space involved. Now, the motion of these gas particles are quite random. In other words, we can't really predict where these gas particles will be, but we do know they have to move in a straight line. Now, inevitably, these particles may collide with each other in that given fixed space of a container. And in that situation, we say that particles collide with each other with their kinetic energy conserved. Another way of saying this is elastic collision. And what this really just means is these particles do not lose speed when they hit each other. Now, normally on the roads when we see two cars hit each other, they usually just stop, and that's when kinetic energy is not conserved. But here, kinetic energy being conserved means these particles will move with the same speed even after they collide. Now lastly, as temperature increases, the average kinetic energy of the gas molecules will also increase. Now remember, conservation of energy. If you give a molecule energy, in here we're talking about thermal energy with temperature, then that energy will be converted to another form, and in this case it's the average kinetic energy. And that's why these molecules will go faster. So what's pressure then? We're probably used to, hearing pressure a fair bit in real life. I mean, all of us are under a bit of pressure from our parents usually. So basically, let's think of it in terms of this analogy. So our parents, they've kind of maybe forced a fair few things on us, okay? And that's how they give us pressure. So in other words, there's an external force, or there is a force involved here. And us, we are basically the object that the pressure is being exerted on, and we have a area. So that's why pressure is equal to force divided by area. Alright, so now we need to talk about the relationship between volume and pressure. So as we can see, when there is a large volume, we have a low pressure. Now why? It's because with a large volume, the gas particles collide with the walls of the container not as frequently. And that is why they exert less force on the given area, and hence there is a lower pressure. Now vice versa. When there is a low volume, we have a high pressure. Because there's a smaller fixed space, the particles will collide with the walls more frequently, and this will cause more force. And with more force, we get more pressure. So in general, we say pressure and volume are inversely proportional. Now, it's good to use terms like inversely proportional because that means as one increases, the other decreases. Okay, chemistry special agents, so your third mission will be to investigate the relationship between temperature and pressure. And at the same time, I want you guys to investigate what is the universal gas equation.